So hey guys, today we are going to talk about HTMLRAG. So from the paper's name itself, you will get to know what exactly this concept is going to be. That is HTML plus RAG, right? Now the headline that they wrote that HTML is better than plain text for modeling retrieved knowledge in RAG systems. Now, working on HTML, at least on the table parser side, I have been working closely on this concept from I think in the past 6 to 7 months. But exploring the whole concept itself, dwelling every single text and every knowledge that exists in the vector DB as HTML. Let's say for web search or maybe non-web search results, that I have not explored. And the paper is pretty good. I'm telling you guys, and maybe this opens a lot of new ideas for people who are actually working on parsing techniques that will make the document embeddings and the rack systems more better. So yeah, let's dive. So the most important part which they have said is that whenever we are working on a rack system, parsing is the major problem, right? So the point they say is that the web is a major source of external knowledge used in rack systems, and many commercial systems such as ChatGPT and Perplexity have used web search engines in their major retrieval systems. Now, what has been the problem? The problem has been, however, utilizing HTML presents new challenges. HTML contains additional content such as tags, JavaScript, CSS classification, which brings extra input tokens and noise to obviously the RAG system. So, to address this, they have proposed this HTML cleaning module. They have proposed compression. They have proposed the pruning strategies to shorten the HTML while minimizing the loss of information. And specifically, we designed a two-step block tree based pruning method that prunes useless HTML blocks and keeps only the relevant part of the HTML, right? So they have experimented it on multiple datasets and they have shared the results with us. So yeah, that's really good. Now I think we can directly deep dive to what they are saying. So introduction is pretty much clear. They are talking about what is LLMs, what is traditional RAG pipeline, and I think we all already know. To people who are not familiar, I'll give you a very brief diagram. Okay, let's say you can take an example like that. You have a system. Let's say I'll take this pen. Yeah. So let's say you have a system. This is your database. Database. This is a vector database. Okay, vector database. You get a document. Okay, you get a document. Yeah. Let's say you have multiple PDFs. You have 3 PDFs, and these 3 PDFs you index it into a vector database using a parser, and this obviously create the embeddings in everything. And whenever a query comes, the cosine similarity, let's say a cosine similarity will be used to match the most relevant, let's say top k results from here, and along the query and top k results will be passed to a LLM, and you will get your answer. Okay, so you will give the reference answer, you will give the query, and the model is going to produce some output from it. Okay, cool. Now I think moving to the information loss in HTML plain text, they are saying. So I think yeah, this is a very good example. If you see this PyTorch documentation, right, you can see here pretty clearly that is tensor, is storage, this everything, that table is there, and you see there is a lot of information which is actually not needed. Just tell me what is the use of these tags which are completely outside and don't have any much relevance, right? So this is a very much important thing to cover up, because if useless information is going, then it's of no use to us, right? And it's only going to increase the size and the complexity of the system. So they are saying, however, employing HTML as the knowledge format for LLMs also presents the challenge that of handling longer input sequence and noisy context. So this should say our experiments show a real HTML document from the web contains over 80,000 tokens on average. Just imagine 80,000 tokens on average, among which 90% of the tokens are CSS styles, JavaScript comments, or other meaningless tokens. So if we clear them out, then we have a very short actual content, right? And that is what they say. Compared to the common maximum context window of LLMs, which ranges from currently 32K to 128K, I think Gemini took it to 1 million, and individual document length of 80K is unacceptable, right? Obviously. So they come up with this concept of HTML cleaning module to remove semantically irrelevant content and we also adjust the HTML tree structure without losing semantic information. For example, merging multiple layers of single nested HTML tags and removing empty tags. So they say these processes reduce the length of the HTML to 6% of its original size. Let's say if that was 100k previously, if that was 100k, it literally got to 6k. Just imagine, from 100k to 6k. So you have removed 94% of irrelevant information, right? So they say that we also further design the HTML pruning module. What exactly is a pruning module? A pruning module which functions upon the intrinsic tree structure of HTML. The pruning process is comprised of the following stages. They say building a block tree, pruning blocks based on text embeddings, and generating fine-grained block pruning. Don't worry, we are going to talk about this in the upcoming diagram in detail. Overall what they are saying, I'll tell you this: generative fine-grained block pruning. Thus, we further develop a generative model to prune the HTML over fine-grained blocks. This generative model is supposed to calculate the score for each block, which is given by generation probability of a unique sequence. I think we all know about logits, right? Something similar to that. Okay. Now, in related work, they talk about RAG. I think we can skip this. Post retrieval process, they will talk about, I think, chunking and okay, abstraction models, and you have the re-rankers here. Okay. Then you have the structured data understanding. Okay, cool. So I think in the methodology you can see what are they saying. Taking HTML as the format of external knowledge presents a new challenge that we have already told. More specifically, we delete less important HTML blocks with low embedding similarities with the input query. Okay, this is where the main point comes, right? So I'll give you guys an example. Let's say the query was who is Sachin. Okay, who is Sachin? Now this was the query. Okay. Now suppose our tree was something like this, and this we have multiple leaf nodes, right? Now if you see, this particular one is about, let's say, cars, and let's say this is about vehicles, something like that. Okay, let's take, so just imagine that if this is the query and this is the whole tree, right? So sort of you can say vehicle and cars one is completely irrelevant, but how are you going to calculate? They are saying they are going to use the low embedding similarities with the input queries. Okay, and let's say this is very less, this is very less, let's say this has a very less importance, right? So this whole block itself will get deleted. Okay, we can remove this block, because what is our main focus? To get good data, understandable data for the model, and not have any irrelevant data which is of no use to us, right? So that's the main purpose. Cool. I think coming to the next part, HTML cleaning. Yeah, how are they doing this? So they have defined this in two things: HTML content cleaning. So they are saying HTML documents retrieved from web contains a large amount of extra data like HTML tags, CSS, JavaScript. So the specific cleaning steps, which are almost lossless, are as following: we remove the CSS styles, comments, and JavaScript. We clear lengthy HTML tag attributes. Okay, these two things are pretty much easy to do. Lossless structural compression. We find that in most HTML documents, their original HTML structure contains redundancies. We can conduct the following compression. What compression? We merge multiple layers of single nested tags. Okay, they have given a very good example here. They say that we simplified the paragraph, some text here, and then you have another closing paragraph and this. So we can do this to this, right? What do you guys think? Because if you see, this is we remove the empty tags such as p, right? So these are not needed, right? These are not needed here, so that can be removed. Cool. Now coming to the third point, which is the most important one. They are saying we are using a granularity adjustable block tree construction. What is this? Okay, what is the problem? To prune all retrieve HTML as a whole, we first concatenate all retrieve HTML documents together and use beautiful soup to pass that HTML documents to a single DO tree. Okay, cool. Now a lot of people are going to think that, okay, what exactly is this tree part that is coming here? See guys, whenever we talk about web development, right, I think most of you have studied about this in your university. There is a thing called DOM tree. What is DOM tree? Okay, that is a document object tree. Okay, I'll give you an example. Yeah, I have got some space here. Cool. So A DOM tree is something like this. Suppose this is the first thing, right? So this will be considered, would be considered a document. Okay, then you will have your root element here. Okay, a root element here. Inside this you will have multiple elements, one, two. Inside this you will sub elements, the attribute element, and then inside attribute you will have text element. Okay, something like that. So you can consider this as a document object tree. Okay, that is what is a very important concept of this whole structure if you talk about. Okay, so they are saying that we propose an optimized tree structure that models HTML, which is not so fine grained ideally. The granularity of the tree structure can be adjusted for different pruning requirements. Why we term it as block tree, and we set the maximum number of words per block, max words, to control the granularity of the block tree. So this max words, right, they are doing it for a purpose, right? Obviously you don't want a very long context thing for you, because then you have to pass it to a small a language model for getting some similarity and everything, and then if the context is too long, it will not be possible for you to pass, right? So they will be passed into their parent and treat them as a block. They are saying we can recursively merge blocks or child nodes into the parent to form a bigger block under the condition that the number of words in a block does not exceed max words. Obviously you can keep merging, even parent and child if the similarity is good and you have the relevance there, but it should not exceed the max words, right? So the algorithms are detailed in appendix B. We will talk about that in the at the end of the video. So yeah, now moving forward, I think we have a block tree HTML consisting, yeah. Now block tree HTML based pruning. Okay, the most important 2 points, right? Pruning blocks based on text embeddings. What are they saying? A straightforward idea is to extract plain text in the block and calculate a similarity score with the users using text embeddings. We have already talked about this, right? Then we use a greedy algorithm to prune the block tree by deleting low similarity blocks and retaining higher ones. Okay, we already talked, right, that if this doesn't have the similarity score, a good similarity score, it will be removed, right? In practice, we keep deleting the blocks with lowest relevance score until the total length of the HTML document satisfies the context window is set. Okay, let's say this whole tree was of let's say 400k words. Okay, and the context window is of only, let's say, 50. Okay, I'll take a very small 20k. Okay, let's take that. Even the 120k is the ideal window right now for GPT, I think, models. So if you remove this, this will become, let's say, 200k. Okay, if you remove these, it will become let's say 100k. If you remove this whole block, it will remove maybe become 30k. And if you remove this will become 20k. Okay, so this is how you will keep reducing until you reach a certain point. Okay, now after block deleting, the redundant HTML structures will reappear. So just readjust the HTML structure, meaning multiple layers of single nested layer tags are merged and empty tags are removed. So yeah, the same thing is happening here. Generative fine grained block pruning. What is this? To further prune models with a fine granularity, we expand the leaf nodes of the prune blocks and get a finer grained block tree. What are they? Specifically, the sequence consisting of tags starting from the root element and walking down to the blocks tag, we term this sequence as a block path. Okay. In the inference phase, the generative model follows the structure of the block tree and calculates the scores of blocks in the block tree. The scores of the blocks are derived from the token logits as displayed in figure 3, and at last the same block pruning operation as we mentioned. Cool. We'll talk about this. Let's understand this structure. You have your model, you have the documents. Okay. Now these documents, the HTML documents, you will do HTML cleaning. Okay, you will do a looseless structure compression. Then you will have some clean HTML. You will do some merging. Then you will have some block tree. Then you will do text embedding based pruning. The ones which don't have good score will be removed. Basically pruned HTML. Fine grained block tree you will have, and then again you will do a generative fine grained block pruning. Okay, and then finally pruned HTML. You will pass this to LLM along with your query, and you will get your answer. Okay, cool. Sounds easy, but obviously encoding that must not have been easy to think about this answer. Coming to figure 3, what was this thing? This is the basically pruned HTML document, right? Where things have been removed on the basis of similarity score. Now in this, if you see, they build a tree, they get a block score, they calculate the block score, the token logit that we were talking about, according to the block tree is transformed to token tree with a tokenizer, and the corresponding HTML tags and tokens are marked with same colors. Okay, cool. Now the token generation probabilities are in the upper right corners, and the tokens in the dash box do not require inference. Okay. So in the upper right corner of the block tree, the block probabilities are displayed, which can be derived from the corresponding token probabilities. So it's pretty much clear. They have explained it, I think, in the most appropriate way in this caption only. So because if you see that you're tokenizing, you're calculating the block score, and then you're understanding which ones are good for you. Okay, cool. Now training a path over generative model. Obviously, this part is important. The prompt for the generative model. You are going to give the HTML, the question, and what you are going to tell the model is to identify the most relevant text piece of the given question in the HTML document. So, and you will also be asking it to give you the block path of that, right? Because block path is pretty much important. Now, what is going to be the output? The historical 2008 Royal Rumble and Shinsuke Nakamura won the men's Royal Rumble, and this is going to be the block path. HTML1 body, div2 paragraph, and similar ending. So they are telling that how have they trained it. So I think this is pretty much easy. You guys can go and read. For that logits thing, I think they have given the same thing here, the efficient tree based inference with dynamic skipping. Okay, yeah, this is also important because if you see, during inference, the generative model is supposed to calculate the block scores, obviously, right? And the score for block B is score B. Each token has a block path, and we first tokenize it to tokens. So, given the model's input sequence, input n-1 already generated tokens, the generative model gen model calculates the logic on the nth token. Cool. And this is the score that they are taking, the exponential of the logits and the exponential of logits, otherwise n equals to 1 or k is equals to 1. The first two condition, it is needless to infer with the generative model, meaning many tokens can be skipped. Cool. Now coming to the baselines, what have they done? They have said that baselines are mainly on the plain text or markdown format. We select 3 chunking based definers and uniformly follow the chunking method in LangChain framework. Okay. And they have used 3 rankers, BM25, BG, BI, the BG large and with encoder only structure, E5 Mistral, an embedding model based on LLM Mistral 7B with decoder only structure. They have abstractive refiners, long LLM Lingua, and an abstractive model of Llama 7 billion and the Jina AI reader. Okay. And an end-to-end LLM with 1.5 billion parameters has been trained. Cool. So they have used, I think, 5.3 for this, I remember. Yeah, 5.3. Let's come to the results, guys. We have talked a lot about the research paper now. HTMLRAG, if you see, has, let's say, on these 6 datasets, has tend to outperform almost in all cases all the other methods. The re-ranking methods, the abstractive refiner method, 71.75, 33.31, 43, 91.75. These are hit at the rate 1 and the exact match. So I think you all guys already know about these matrices because these are the most famous RAG matrices that they're using, and I think they have already defined these matrices, I think, here. Yeah. So what they say is, yeah, they have the evaluation metric is to performance of RAG. So we evaluate LLM's response as the end-to-end result. We choose different evaluation matrices for hotspot QA, and in which each question is annotated with a single short answer. We report exact match. Okay, that is EM. And hit at the rate 1 means at least one answer of the annotated answer finds the exact match in the LLM's response. Cool. And I think even for Llama 3.1 billion model, we get almost in all cases HTML RAG, and similarly for 3.170 billion, I think, except these 2-3 cases, this is sort of, you can say, a tie. We are getting the best results for HTML RAG. But yeah, if you see the results of HTML RAG without pruning and baseline under the long context setting, you will see that, okay, in that case, maybe we are not getting that good results. Vanilla HTML, the plain text, only text in the markdown, and HTML RAG without pruning. Okay, so you will see a lot of bad text is going here. A text the text that we actually don't need, and you'll see the difference in the quality, right? So this is true, right? I think that paper from Microsoft, textbooks are all you need. A good data is very much important for your model to perform well on it, right? Similarly, experiments result for the impact of block tree granularity. The results of prune embedding and prune gen are represented in a bar chart. So I think you guys can go and read this. We try to make, make the video as short as possible. We have already taken, I think, more than 15 minutes. So yeah, and I think this is the algorithm. You guys can go and read this. This is a very good algorithm. I think people who have done data structures and algorithm will be able to understand what exactly is happening here. We use a queue, and till a point we don't satisfy, you get a satisfaction, we keep doing it. There is a condition that is, if that is not satisfied, that queue will not end, because we will keep putting more and more elements in that queue. Okay. And yeah, I think that was it for the paper, I guess, guys. So hope you guys learned something new from this paper. I would, as usual, give the link to the paper in the description. You guys can go and read it from there. So thank you and have a nice day.